Hi there again. We've talked about root finding several times in past videos, focusing primarily on implied volatility, inverting the Black-Scholes model to pull out implied volatility, and we also just looked at coming up with some generic functions and finding the roots of that. And we did that by coding Newton's method by hand, which is fine. However, Python's NumPy library and other numerical software packages like MATLAB have built-in root finding commands. So I wanted to go back quickly and look at the same problems. We're going to just use the same generic function that I used last time, as well as the implied volatility problem. And in a Jupyter notebook, we're just going to code up something quickly and use the NumPy, or SciPy actually, function fsolve to invert the equation and pull out the roots of the equations. So with that, let's get started and move on over to the Jupyter notebooks. So I'm going to do this in a Jupyter notebook, and we're going to need NumPy, and we're going to need the fsolve function from SciPy. So from scipy.optimize import fsolve. And I am also going to import the plotting library matplotlib. So import matplotlib.pyplot as plt. And then we're going to have to do this matplot. Let me make this a little bigger so it's easier to see. Matplotlib inline. Okay. So let's use the function I talked about last time. That was an exponential function. So it was, let's just define it here, we'll call it f of x. And it was return np.exp of x minus 5 times x. So let's just plot that and see what it looks like. So let's define our x values. Let's do x is equal to np.lin space, and let's go from minus 5 to 5. Y is going to be f of x. And let's do plt.plot x comma y, and we will make it a black line. So that's what our function looks like, and you can see it has two roots. So let's find this the root on the right hand side. So let's come back up here. Where do we want to do this? Let's do it before we plot it. So add a couple spaces in here, and let's go results equals fsolve, our function f, and we need to send an initial guess. So let's just send an initial guess of, I don't know, let's just say 5. And then let's just print results. Let's run that. So here's our result, about 2 and 2.5. That looks about right. Let's just plot it on this plot. So let's go down here and let's go plt.plot results 0, the first element of that vector. In other words, fsolve returns a vector, and let's have it do f of results 0. And let's just make it a black circle. So are we good? It looks like we're good. Let's run it. There's an error. Where is the error? Error. Oh, I wrote plot, plt.plot. So there we are. Yeah, that works pretty good. So we could use this if we wanted to use a canned routine to find a root rather than write in our own code. And this code can automatically or numerically find the derivative of the function, which is needed to do this type of process, just like we needed the derivative for our Newton's method. This is done numerically here, but we could also provide an explicit formula for the derivative. So why don't we just go back to the implied volatility problem and just quickly run through that with fsolve. So in a new notebook, I've imported NumPy, I've imported the probability distributions here in from the Scipy stats library and our fsolve function. I'm going to do the matplotlib library as well. And in my original code, if you have actually looked at it, I used here I used the built-in math library, Python's built-in math libraries, and I'm just going to do the whole thing in NumPy this time. So here in this cell, I've just copied over the function for calculating the D1 and D2 values, and just modified them to use the NumPy math functions instead. So let's do the same for the price of a call, Black-Scholes price of a call, and we'll do price of a put too. So here's the function for the call price, here's the function for the put price as defined by Black-Scholes, and it's the same code as I've used before. I've just, again, explicitly using the NumPy libraries here. So let's move on to our values of strike prices and stock prices and whatnot. Before doing that, let us actually write the function that we're going to pass into fsolve. And before I called it f in the previous example, so I'm going to call it f here. And we should probably have a more descriptive name for it, but we'll just stick with this. So this just calculates the Black-Scholes price minus the actual price off of the option chain and returns that value. So this is going to be for a call option. So now let's visualize things, and let's put in the parameters we're going to use, and let's put them in a new cell here. And these are the values we used in the original video on implied volatility. So we have the stock price of 100, strike price of 105, 30 days to expiration, and it has to be in years, so we divide it by 365. Risk-free rate we had is 1%, and the actual call price from the option chain was $2.30. So let's visualize what this looks like as a function of volatility. So this function f as a function of sigma. So let us do sigma equals np.lin space, we'll go 0 to 1. So we'll do 0 to 100% volatility. And let's plot plt.plot sigma. Let's see if I spelled it right. Sigma. And then let's pass in that to this here. So sigma and our function, and let's make this a blue line and run. What is the issue here? I probably need to rerun this cell, so run, oops. Okay, I just deleted those cells. Let's go back up here, run this cell. We can come down here and now run this, and there we go. Let's add in a line here at 0 just to visualize this a little better. So let's put in a command here, plt.plot. The x values will be 0, 0. So there we go. The x values are 0 and 1. The y values are 0, 0. And let's make it a black line. And we're looking for where our implied volatility curve crosses this 0 value right here, which is about 38%, 0.38. So solving this now is just as easy as making a call to fsolve. So we're going to do vol equals fsolve. Our function is called f. We need an initial guess. I'm going to do 0.5, and we need to pass in all the arguments that the function takes. So that's args equals, and let's see what those arguments are. How did I structure this? So let's just copy and paste this. There we go. Copy. Paste. And let's see. Let's go down here and print vol. So there it is, 36.8%. So that's what our other code gave us, which is not surprising. And this will have the same issues within the money options if the intrinsic value is, if the option price is less than the intrinsic value. So if we were to go up here and set this strike price to 90, let's run this cell and let's plot it. Again, notice that we're not crossing zero. This function has no root. So if we go down here and we try to calculate this, we get an error. So it's going to have the same issues as before. So if you're actually going to use this code for anything, you know, in some sort of production environment, you're going to have to address that. So let's go back here and make this back to, what did I have it before? 105 was it? 105.0. And fsolve needs the derivative of the function. It calculates it numerically. But if we wanted to make this code a little bit faster, again, if you had tons and tons of data to process, you might want to do this. You can pass in the derivative of this function, which is our Vega value. So let's just modify that. Let's modify this to do that. So let's go back up here to this cell where we defined all these functions, and we're going to create another function here called Vega. So def Vega, and it's going to take the same arguments as here. So copy, paste. What the hell happened? Okay, there we go. And let's go down here. Let's calculate our Vega value. Let's not just use the same name as the function. Let's call this, oh, I don't know, let's just call it V. And return V. And it needs to be a list-like object or array-like object, so I'm just going to wrap it in brackets. So that's our Vega here. So let's go down back to this fsolve thing. Did I reset these? Let's actually run this cell. So run that. Let's make sure these values are up to date. And let's replot it. Are these not updating? There we go. Back down here to fsolve, and let's put in here, we need to pass an f prime. Did I spell it right? Yes, I did. And that's equal to our Vega function. So now let's run this. Error. D1. Oh, I need to calculate the D values, don't I? In that Vega function. So let's go back up here. And where's my D function? Copy. Go down here. D1 comma D2 equals. And that should do it. Run that cell, run that, just make sure everything plots. Still an error. Oh, I need to, what do I need to do? That needs to be np.square root now, right? np.square root, run. Yay, there we go. So now we're passing in the derivative. It's a useful thing to do if you can get away with it. Sometimes it's not practical. It's either too complicated or not able to be calculated by hand. So you have to let the computer do it. But if you can get away with, if you can actually do it, you often get a runtime performance boost from that. So this ran longer than I thought I was going to. I have a tendency to run long apparently, but so I'll just call it quits now and say that I will clean up the notebook and upload it to GitHub, and until next time, later.